Oh, okay. Got it. Wow, I wasn't expecting that to appear over there. I think. I think this is recording. I don't know how to get rid of this thing in the corner here, but okay, we'll see. We'll see how this whole thing works. This is do I want to zoom in on me? Wow, look at this. That's me. Oh my goodness. Okay. This feels strange. Wait, I want to follow me. Okay. Well, it's Friday. Happy Friday, everybody. Week 2, Friday. And how's your quarter going so far? Good. All right. I got some thumbs up. That's great. Yeah. And if it's not going okay, I hope you have friends and family and support. Someone to talk to. Get your sleep. It's important. Okay. All right. Important sampling. This is the topic. This is the topic of the day. We brought this up. We introduced this Wednesday. And the idea is that we are frequently, especially in the context of Bayesian statistics, we often want to know, what is the expected value of some probability if, what's the expected value of the probability if the probability itself, like the parameter is a random variable, right? So we've been talking about in the context of the beta binomial model when we're talking about, what's the probability that the batter is going to get 2 hits in the next 3 at-bats, or, this outcome is going to happen. The question is a lot more complicated when the batting average, when that number is not a constant, okay? Everything else, your stats 10, your early intro stats, you always treated that batting average, that probability as a constant, but now we're treating it as a random variable. And that's what happens in Bayesian contexts. And so in order to get that answer, what is the probability, or what is the expected value? The expected value of some function applied to a random variable, okay, is going to be equal to the integral of the function multiplied by the PDF of the random variable. And this integral, a lot of times, is difficult to calculate. So we're going to estimate it using Monte Carlo integration, or Monte Carlo estimation. We just draw random samples from F, draw random samples from that PDF. We apply the function to those randomly sampled values, and we take the mean. And that's a simple process. I think it's rather straightforward. You guys have already done that in your homework. The problem sometimes that we run into is that we're not able to sample directly from some function f. Okay? And so the solution that we're going to do is run importance sampling. We're going to say, I am not able to sample from f directly. I'm going to sample from some other distribution, and that's what importance sampling is. Okay. The other option is, well, figure out some way to sample from f directly. Figure out some way to sample from f directly. We have a bunch of distributions built into R, and we've been using those so far. But what if we want to sample from something that's not one of these built-in distributions? Okay, we'll take a look at that next week. So today we're going to say, instead of sampling from f, I'm just going to pick an entirely different distribution G. So f might, have one shape, and we're going to sample from a different a different distribution, okay? And again, the only requirement is that anywhere where f is not 0, g is not allowed to be 0, okay? So you can't have a probability distribution. You can't have a random variable g or PDF g where it's 0 someplace where f is not 0, okay? So as long as this condition is met, we can do this. And mathematically, we said this is how it works. The way it works is I'm just going to take this integral, multiply it by 1, which I'm allowed to do, g of x over g of x. And again, as long as g of x is not 0, or f is not 0, okay, as long as this thing does not equal 0 anywhere inside of x, then we're okay. I can kind of rearrange terms. And this is back in the form of arbitrary function times a PDF integral of that, okay? Integral of some arbitrary function times a PDF. It's just that our arbitrary function looks a lot more messy. It's h of x times f of x divided by g of x. It's the original function, the original arbitrary function h, multiplied by basically a ratio between two PDFs. F is some PDF that we were not able to sample directly from. G is a different PDF that we are able to sample from. And we have basically a ratio between two PDFs, but it's just we can just treat this as an arbitrary function. H of x times f of x divided by g of x. Some arbitrary function times a PDF. We take the integral of that, and this is equal to the expected value of this thing, and these two things are equal, okay? And so the notational difference is the expected value of h applied to some random variable x, if x has PDF f, is equal to the expected value of h times f over g applied to a random variable x, where x has the PDF g, okay? That's what this little subscript means, okay? This random variable x has a PDF g, whereas this random variable x has PDF f. Okay, that's the difference. That's the difference here. Okay, so that's mathematically, that's what we say how it works. And then the process in which we do this is kind of the same process. It's just, what is the function we apply? It's just a messier function. So now we're going to just say, generate a bunch of values drawn from PDF G, drawn from some arbitrary PDF that we are able to sample from. And then calculate this function. Calculate h applied to that x value. Multiply it by f applied to the x divided by g applied to that x. And then take the mean of all of those numbers. Take the mean. Take the sample mean. And that is going to be equal to the expected value of h applied to x if x came from f. And again, that seems like how? But somehow it works. So here is a silly example. Silly because this is a completely contrived situation. So we're going to say, okay, so we're going to draw random values from G, but we want to estimate the expected value of a function h if x came from f, okay? So we're going to pretend that f is a beta distribution with shape parameters 2, 4. And again, we're going to pretend, and again, this is silly, but we're going to pretend that my computer is not able to generate values from the beta distribution 2, 4. But we are able to generate values from this distribution, beta with shape parameters 5, 3. Okay? I guess maybe another scenario that is equally odd. You could imagine, let's say we went back 50 years or something, where we have a computer that's able to generate values, but you have to like request time and it's expensive, right? And then so you say, hey, I want this computer to generate values from the beta distribution. And I want it to come from the beta distribution 2, 4. But whatever, the operator messed up, you know, comes back 5 hours later and says, okay, I did what you asked. Here's a bunch of values from the beta distribution with shape parameters 5, 3. And you go, no, these are the wrong parameters. What am I going to do now? Okay. Do you just throw these away? You could, and request that it rerun. Or you could just say, all right, well, let's just take these numbers and can I use them, right? So what if this is what you have? You got values coming from this distribution, beta distribution 5, 3. You wish the numbers came from this distribution, beta with 2, 4. Okay, silly situation, but just stick with me, okay? And these are the two distributions, okay? So this is the distribution we want. Shape parameters 2, 4 would have a peak somewhere around here, okay? Its mean is something like 0.33, right? This is the distribution we want. We want the distribution in blue. What we got was the distribution in red, okay? Can I still estimate values? Right, and the answer is yeah, we can. We just have to basically adjust everything, do adjustments based on these values, right? So over here, so what we have is the red curve. What we have is the red curve point with a peak something around 0.7, okay? 5 out of 8, so something around there. With a peak somewhere around 0.7, and what we want, we're getting too many values around 0.7, okay? Compared to the blue, right? How often does the blue distribution produce 0.7? Not very often. How often does the red one? Way too many, okay? So whenever you see a 0.7 come along, you go, we're gonna dial down your importance. You're not as important because we have too many of you, okay? Over here, how often does the blue produce a value of 0.2? Blue produces 0.2 very frequently. So we want lots of these, okay? Our sample does not produce values near 0.2 very often. So anytime we see a sample, a value near 0.2, we need to magnify its importance, okay? And that's what this importance weight is doing, okay? So again, just to kind of reiterate what we're doing, the mean of the F distribution is 0.33. The mean of the G distribution, that is the red one, is 0.625, okay? And let's say I wanted to estimate the mean of the blue distribution, okay, using Monte Carlo, okay? Well, Monte Carlo methods, we would just generate our random sample and take the mean, and that would be an estimate of the mean. Here, my sample X is coming from the wrong distribution. It's coming from the beta distribution with shape parameters 5, 3. Okay, I generated 100,000 values, 10 to the 5. What's the mean of X? The mean of my sample of 100,000 values is right around 0.625 because guess what? It came from this distribution, 5, 3. But we want to get a mean that's closer to this, okay? And so what we do is we apply the importance weight. We're going to take each of those values and we're going to multiply it by F over G, okay? It's basically what we have right here, right? We're going to just multiply by F divided by G. And as long as G isn't 0, we can do this. So again, if we look at our picture, the red distribution produces way too many values at 0.7 because the blue one doesn't produce that many. The red distribution doesn't produce enough values around 0.2. So if we look at a value around 0.7, what is F? The blue distribution's 0.7, okay? At 0.7, the blue distribution has a value of something maybe around 0.4, and the red distribution is something maybe around 2.3. I'm making that up, okay? So 0.4 divided by 2.3, we're going to get a value less than 1, okay? We're going to weigh this less. So the weight at 0.7 is going to be less than 1. Okay. On the other hand, if you look for values near 0.2, F, the blue, has a value of around, I don't know, 2.1, whereas red, its value is something around 0.2. Okay, so blue, F, has a large value divided by G, the red, which has a small value. This value is going to be much greater than 1. So we're going to magnify its importance. Okay. So I don't know. So let's say you wanted to get some general, you wanted to do a survey, or you want to know like what's the campus opinion about some topic, okay? And you say, okay, you know what? And you look at your circle of friends, and maybe your circle of friends, most of them are stats majors. You have a couple, maybe friends who are econ majors. Maybe you have like one friend who's in the theater school, or one friend in some other North Campus humanities major, right? Maybe most of your friends are in the sciences or South Campus majors. But if you look at kind of the distribution of, who's majoring in what at UCLA, it probably doesn't look like your own friend group, right? You look at your own personal friend group, it's probably not super reflective. I don't know, maybe you have I don't know what your friend group looks like, okay? But the people that you regularly talk to and things like that, perhaps it is not as representative as the UCLA campus, okay? I don't know, maybe if you're living on campus housing, you get a bit more of a broad range. So what you might do is, if you can only talk to your group of friends and you're trying to guess what the overall campus opinion is like, you probably want to talk to, your one theater friend, and you have to ask them like, hey, tell me as much as you can tell me about the rest of the theater school and things like that. And you're going to take whatever they say and you're going to kind of weight their opinion a lot more heavily, right? Whereas each individual, right, let's say you have like 6 friends who are stats majors, you're basically going to take all 6 of them and compress it down like into basically one opinion about like the stats department, right? And so, you might have like varying opinions within the 6 stats friends who are stats majors, but you're going to kind of like weight them a little bit less because you just have so many of those opinions available, right? And so it's kind of like in order to kind of balance out for how your I guess sample of friends is kind of biased versus the general population, you kind of do this importance weighting, okay? And that's what this is kind of like, right? We say, well, what is it that we want? This is kind of what we're aiming for. We want F, what we have is G, okay? How does F and G compare at these different values? So in some places, you get too many G and not too many G compared to F. So you're going to weight those down. In other places, you get not enough. So you're going to weight those more heavily. I think, question. Yeah, so we haven't really talked about how random sampling even works. Right now, it's just been like the computer, you type in this thing and you get a random sample, okay? So there might be situations where the PDF of F is defined, okay? Or maybe it's not even defined. It's just, we'll just say we have the PDF of F defined somewhere, but for whatever reason, we're not able to draw samples from it, okay? And we haven't talked about how to generate random samples in the first place. And certainly what we'll look at next week is we'll say, if you have the PDF of F, there's lots of ways we are able to generate a random sample from F, but for whatever reason, we're not able to. But yes, we have to be able to calculate f of 0.7. That is, what is the PDF, which is different from generating a random value, right? We haven't even talked about that. We're just assuming the computer is able to generate random values, but we haven't talked about that. But yes, we do need to have the PDF of f. We do need to have the PDF of g, and in order to calculate kind of this importance weight. So right now, because we haven't even talked about how random sampling works, it's difficult for me to give you like concrete examples. But I will say, generating a random sample is not a trivial thing. It's a little bit hard. And certainly in coming weeks, there will be situations where we don't even have the PDF of f fully defined. We only have something proportional to the PDF of f, okay? We'll have something proportional to the PDF of f, but the actual PDF, we might not know, okay? It's kind of like when you found the PDF of the beta distribution, you had to kind of figure out that proportionality constant in the front. You know, it's like gamma alpha plus beta over gamma alpha, gamma beta, something like that. And it's kind of a pain to figure that out. And sometimes we can't figure out that proportionality constant. We just have some function that if we integrate, we know it should integrate to 1, but we don't actually know the proportionality constant needed to make it integrate to 1 because it may be a highly complex one. But yes, we do need to be able to figure out what f is. We do need to figure out what g is. Okay, so the PDFs in R, to calculate the PDF, we use the d, right? The density function, right? We're using the probability density function. So we're going to do d beta. D beta for f is d beta of x, shape parameters 2, 4. D beta of g is the PDF of the beta distribution with shape parameters 5 and 3. Have I given you any view quiz answers yet? No, none. Okay. First one is B. B as in beta. B is your first view quiz answer. So this would be my vector of weights. So I've got 100,000 values randomly of random x values drawn from this beta distribution. I have 100,000 of those things, and I'm going to calculate 100,000 weights. I'm going to calculate the weight for every single x value I've drawn. So I've got 100,000 weights to calculate. And I take the product between those x values and their weights. And when I do that, and I calculate, say, the mean, this mean is very close to the theoretic mean of 0.33 for this beta distribution. Okay? So the significance of this is to show that when you take your x values, which were drawn from the wrong beta distribution, if you weight them according to this, is just the ratio between these two PDFs. If you weight them accordingly, you can calculate the mean, and the mean is equal to as if you drew 100,000 values from this beta distribution. Okay, because the other beta distribution should have a mean of 0.33. We're using the same x values, right? The original mean was 0.625. When I weight them accordingly, I get very close to 0.33, 0.3329. And again, just to show this is not some trick here, if I take the actual x values and I create a histogram of the x values, the histogram of the x values fit the red line, which is g, and not the blue curve, which is f. But we're getting an estimate of what the mean of the blue curve would be, or the expected value of the blue curve, which would be 0.33. And all we've done is we've just weighted each value. We've weighted them accordingly using the ratio between f and g. Okay, let's try another example. And again, these are all kind of slightly silly examples because a lot of our computers are very capable of generating random values for us. Okay, but we can still do this. And well, hopefully you'll do an exercise in your homework 2, where you do some important sampling and you'll see how it performs. Okay, so here we're going to look at something called the folded normal distribution. Okay, so what if you have a normal random variable, but then you took the absolute value of it? Okay, so basically you have basically just half of the normal distribution, but it's twice as tall because it has to integrate to 1, right? So we're just taking the normal distribution. This is the PDF of the standard normal, and then we're making it twice as tall. Okay. You can actually have folded normals of not the standard normal distribution. Like you could say, what if I have a normal distribution with mean 2 and standard deviation 1? Okay, so like, 97% of it's on this side, but then you have like this little tail, and you can fold it over, and then you'd get some adjustment. So basically, we're just taking the normal distribution, we're folding it on some axis here. But anyway, here we're going to do the standard normal, and we're going to fold it in half. And so this is very easy to picture. We have basically the PDF of the normal distribution only where x is positive, and it's going to be twice as tall. So the support of x here is going to be from 0 to positive infinity. And the question is now, what is the expected value of this distribution? Expected value of the normal distribution is 0, but then if you take the absolute value, what's the expected value of that? It's a lot harder, okay? Now, we can, this would be very easy to do the Monte Carlo way, right? I would just say, give me a random normal variable. Just give me like 1,000,000 values from the normal distribution. I'll take the absolute value, and then I'll calculate the mean. Boom, done. Okay, there's your estimate. But we'll use important sampling just so we can show off our new technique. Which is pretty much what all of these lectures are, right? Like, here's a new technique, let's show it off. Okay, so again, very easy, we can do this, right? Just generate 1,000,000 values from the normal distribution, take the absolute value, take the mean, and we get 0.79738, okay? And that's a good estimate for what the mean of the folded normal distribution is, okay? But we're going to pretend we can't do this. We're going to pretend we're not able to generate from the normal distribution. Which, by the way, was not a trivial thing either, okay? We just say, hey, our computer is able to generate values from the random normal distribution, but would you be able to do it? You could kind of do it if I give you an inverse normal table, but anyway. Okay, so this is what we're going to do. What we will do is we're going to generate values from an exponential distribution. Okay, we're going to say, hey, the PDF of an exponential distribution is lambda e to the negative lambda x. And, if we look at this, let's use lambda equal to 2. We could have done it, used other values, but this will work well. Okay, so we're going to do 2e to the negative 2x. This is going to be the distribution that I will generate values from, okay? So the support of G contains the support of F, in that if you think of what is the support of F, the support of F is all positive values greater than 0, and the support of the exponential distribution is all positive values greater than 0, right? The exponential distribution is used for how long did you have to wait in line, right? Your wait time. Okay, so the minimum wait time is 0, and then maybe you have to wait a long time, okay? So that's the exponential distribution, and we are able to generate values from the exponential distribution, okay? I know we're able to generate values from the normal, but we're pretending like we can't. So we say, all right, let's say I am able to generate values from the exponential distribution. Here is the PDF for the values I am able to generate, 2e to the negative 2x. So we generate a bunch of values from the exponential distribution, and what we have to do is we have to compute these weights, okay, f over g, okay? So the weight for each value that we get is going to just be the PDF of the normal distribution times 2 divided by the PDF of the exponential distribution with rate equal to 2. And using the computer, this is made very easy because we have the PDF function. So the computer is able to give me the PDF of the normal distribution. And the computer is also able to give me the PDF of the exponential distribution. So I just have to do d norm, that's the density, the PDF of the exponential, but I have to multiply it by 2. And I take the exponential and I say rate is equal to 2. Okay, so whatever these weights are, I'm going to multiply it by h. So we're going to take my function. We just want to find the mean. So here the value is just going to be x. Okay, we want to know what's the expected value of x if we get this, all right? So here we go. 1 million values. From the exponential distribution, we're going to calculate the weights. Apply the PDF onto x, apply the PDF of the exponential, and so this will give me the weights, all right? And then I take those x values that I generated, multiply them by the weights, and I calculate the mean, okay? And so the mean I get is 0.7976598, right? We have this value back here where I generated 1 million values from the normal distribution, and we get pretty much the same value, 0.7973812, something very similar to this. Theoretically, the mean is going to be the square root of 2 over pi. So the theoretic value is 0.7978846, okay? So all of these gives us something with about 3 decimal places of precision. Here we generated values from the normal distribution directly, took the absolute value, and took the mean. Here I generated values from the exponential, I weighted them, and I took the mean, and this is the theoretic value. How did I get my theoretic value? That's, I think I've got a slide for that. Okay. If the, what we have here in blue is the normal distribution, okay? It's just, it's half of the normal distribution, okay, but made twice as tall. So this is the PDF of the normal distribution. The red curve is the exponential distribution with lambda equal to 2, okay? So this is the PDF of G in red, PDF of F is in blue, and if you do the blue divided by red, you'll get this black curve, okay? Which itself looks kind of like a normal distribution, but it's not. So over here, where the blue is shorter than the red, the ratio is less than 1, okay? Where the blue and the red are at the same height, the ratio between blue divided by red is equal to 1. And over here, where the blue is taller than the red line, the ratio, the weights get larger than 1, okay? And then it's hard to see, but they cross back, okay? The difference between the blue and the red get bigger and bigger, and then the difference shrinks until they actually cross back. And there's a point where the blue curve is underneath the red curve, and it goes down again. So this is how the weights change for different values here. in order to kind of accommodate that. All right. I guess I'll give you your second view quiz answer. Second view quiz answer today is A as in apple, A. Okay. What if we wanted to do something like this? Okay. What if we wanted to ask, what is the probability? What's the probability of getting a standard normal value that's over 4.5? Okay. So the true answer is we would do 1 minus p norm 4.5, right? So you think, within 3 standard deviations, you have 99.7%. Within 4 standard deviations, you have even more. And how much is beyond 4.5? Like, how many values in the normal distribution are more than 4.5 standard deviations away from the mean? Okay. And this says about 3 in a million. 3 times 10 to the negative 6. Okay, so about 3 values in a million. 3 in a million are more than 4.5 standard deviations from the mean. Okay. If we wanted to estimate this using a Monte Carlo approach, what could I do? One is I could generate a million values from the normal distribution, and I could say how many values are over 4.5. Okay, so when I do this, I have a million values from the normal distribution, and I ask how many values are over 4.5. I have 2 values that are over 4.5. So my estimate is off by a fairly significant factor, right? The true value is something around 3.4, okay? 3.4 in a million, where just my Monte Carlo estimate, I got 2 in a million, okay? It's not wildly off, but again, it's so rare that even after a million draws, this only happens twice, okay? So we can try to improve our accuracy by just sampling a lot more values. So instead of generating a million values, maybe I generate 100 million values, maybe I generate 1 billion values, something like that, okay? Or we can try to do importance sampling. Okay, so what we will do, instead of generating values from the normal distribution, do I have a picture? Okay, so again, here's our, okay, so if you think of the normal distribution here, right, we're basically going way out here in some tail region. We're at 4.5. What's wrong with my pen here? Okay, and we want to know, like, what's in this tail, okay? Another option is I can just say, hey, you know what, what does our exponential distribution look like? Our exponential distribution looks something like this, right? What if I just start it? What if I just started at 4.5? Okay, and if I were to like zoom in here, okay, the tail might look something like this, right? This might be the normal one. And then the exponential might look something like this. Okay. So what is an exponential distribution that starts at 4.5? Okay, we're just going to say, hey, let's do an exponential distribution that starts at 4.5. And all this is okay, how do we do this? Well, we're going to have to multiply this by some constant. Okay, let's just do, again, we got lambda e to the negative lambda x. So let's just use lambda equal to 1. That's fine. Okay. And then, and we're going to just take this and multiply it by a constant so that when I go from 4.5 to infinity, the whole thing integrates to 1. Okay, so we're going to just say, okay, I got e to the negative lambda x divided by some normalizing constant. Okay, so what does this integrate to? Okay, well, e to the negative lambda x becomes negative e to the negative x. We're going to evaluate from infinity to 4.5, okay? When you plug in infinity, you'll get 0. E to the negative infinity is 0. And e to the negative 4.5 is this. And so effectively, e to the negative x divided by e to the negative 4.5 is going to be negative x minus 4.5. Okay, so this is going to be my PDF that I'm using. Is that okay? So that's the PDF, and we're just trying out an exponential distribution that starts at 4.5. Okay, and this is an illustration of the memoryless property of the exponential distribution. You guys remember that? Where it's like, no? So it's kind of like, how long will your light bulb survive? And and you say, well, it's already survived a year. It's still an exponential distribution. The light bulb doesn't have any memory of, it's not like, oh, I already survived a year, now it's time to die. It just, the probability it's going to survive is still exponential distribution. Okay, so what do? Our weight parameters now, we've got the PDF of the standard normal distribution up here. And over here, we've got, so PDF of the standard normal distribution up here. This is the PDF of our exponential distribution just shifted over 4.5. And we just want to know, what's the probability of being in this tail? What's the probability of being in this tail? So I'm going to just generate 100,000 values from the exponential distribution, and I'm going to shift everything over 4.5. Okay. And at this point, what is the h? It's just basically going to be 1. It's 1 for all values over 4.5, and all of my values are over 4.5 because when I generated my random exponentials, the smallest value is 0, and I've added 4.5. So every single one of these is over 4.5. So now I'm just going to weight them according to my weights. I plug in, okay, what is the normal distribution? What is the PDF of the normal distribution for, say, 4.8? What is the PDF in the normal distribution for, say, 4.9 or 5 or 6 or something? And then we will divide that by the PDF of the exponential distribution that was shifted over 4.5. So we're going to do F divided by G. Okay? And when we do that, and again, so I'm just doing W times 1, so it's just W, because this is the function is an indicator function, and it's going to be 1 for all values greater than 4.5, and all of our values are greater than 4.5. So we get 3.375 times 10 to the negative 6. Okay, compare that to what was the P norm? P norm is 3.397 times 10 to the negative 6. So we're getting something a lot more accurate, 3.375 versus 3.397, okay, times 10 to the negative 6. And so using kind of exponential, using importance sampling and the exponential distribution, we can estimate some of these extreme tail probabilities versus using just the straight Monte Carlo approach, kind of this naive approach where I say I'm going to just generate a bunch of values from the normal distribution. All right, do we have any questions? Does that seem strange? All right, let me give you your last view quiz answer. Last view quiz answer is C, C as in cat. C as in cat is your last view quiz answer. Okay, that's it. That's it for today. We'll finish a couple minutes early. Have a good weekend, you guys, and we'll see you guys on Monday.